Next talk will be presented by Professor Steve Ward, Professor of Computer Science and Engineering in MIT Computer Science and Artificial Intelligence Laboratory. Professor Ward is the Professor of Computer Science and Engineering at MIT, whose faculty he joined in 1974. Since that time, his teaching and research have dealt broadly with the architecture of computer systems at both hardware and software levels. Recent research foci have included goal-oriented computing and related variants of conventional computing models. Currently, his primary interest is in education, including the engineering of educational tools, experiences, and concepts. Professor Ward holds SB, SM, and PhD degrees from MIT. The title of his talk is Algorithmic Education. Professor Ward, please.
Well, thank you. Your four visitors today from MIT are all computer scientists, and we're all excited about the interaction between computer science and education. In the deployment arena, we're all excited about e-learning and MOOCs and all of that stuff. And I share that excitement, and we're all involved in various aspects of that. I was encouraged, on the other hand, by Professor Zhu to talk about something that's slightly different, although I think closely related, which is also an interaction between computer science and education, and one that has, in my view, an equally strong impact. It has to do with computer science changing not only the way that we teach, but in a sense, what we teach. So let me begin by talking about our traditional approach to education. Okay? Traditionally, we take kids and we first educate them in sort of a set of core basic skills, reading and writing and math and literature and history and so on. And there's this set of things that we teach our kids all more or less at once. We teach them all at once because they kind of reinforce each other. We use their language skills to talk about problems in science. We use math to deal with science problems and so on. So each of these basic skills plays an essential role in the education of the other basic skills. And once we've done that, in later phases of their education, we go on and selectively to teach them about specialties. We might teach them to be accountants or engineers or computer scientists. So that's kind of the tradition that we've all grown up with and have all kind of believed in. But there is a growing movement that argues that that set of core basic skills should contain at least a piece of computer science. That basically, this idea of that I've been calling algorithmic thinking, the notion of an algorithm as a way of specifying behavior, is a conceptual revolution that is exceedingly important, and that should be incorporated into these into the basic core educational framework. So that's the idea that I want to explore, and I'm, of course, not the only one that is exploring it. What I want to do first is kind of just to be perfectly clear, the thing I'm not talking about, I'm going to name a few things that I'm actually not talking about here. Although all of these things I think are good and I'm enthusiastic about them, but these aren't the topics that I'm focusing on. Okay, the first is sort of the MOOC scene, massive online education. I think that's a wonderful thing. I think it's actually revolutionizing education. It's going to, over the next 50 years, change universities. But that's not what I'm talking about. Okay, there's also vastly increasing use of computerized tools, simulation models and things like that in education. I'm not really talking about that either, although that is related. And finally, there is a strong movement to push programming skills, okay? The idea that we should make all of our citizens, all of our students should be expert in programming. I think that's a great idea. I think programming is a basic and very useful skill, but that's not exactly what I'm talking about either, okay? What I'm really talking about is a conceptual revolution that I think it underpins a certain approach to education. So let's look quickly at our sort of existing models of understanding. We measure our students' understanding in a variety of ways. We feel that a student has some level of understanding if they can describe what it is they understand. Okay? Maybe a slightly higher level of understanding is that they can give a coherent explanation of it. They can, give a little talk on it to somebody else who's naive about it. Okay? A third level is that they can answer questions about it. Now, this is the kind of thing that we use to measure the students' mastery of a topic. We give them quizzes where we ask questions and expect them to get the right answers in order to demonstrate their understanding. There's a fourth level, which is slightly more sophisticated, and that is, if I really understand something, for example, I understand how some law of physics works, I can use it to predict behavior of real-world systems. So the ability to predict behavior is another model of understanding and a way of measuring a level of understanding. Now, all of these are commonly used in traditional education, and they all fit within this sphere of the traditional core. If you have language and math skills, and depending on the topic, science and history or whatever, you can demonstrate all of these modes of understanding. There is another mode of understanding, which actually has been popular for hundreds of years in universities, and is getting a new push from the online education community, and that is teaching as a way of demonstrating understanding. It's closely related to the earlier ones, but it's more and more defended as a piece of the educational experience, to demonstrate that you understand something by doing some teaching of that something. Okay? But finally, there is the new model that is enabled by this algorithmic insight. Okay? If you really understand something, you can program it. Okay? If there is a behavior that results from some interaction that you really understand, you can write a program that emulates that behavior by that kind of interaction. Okay, well, many people refer to what I'm proposing here as computational thinking, and the idea is, of course, not new. We can look at some fairly early traces of it, some of which trace back to Professor Seymour Papert at MIT, who's famous for a lot of things, many of them education-related. He came up with a constructionist model of learning and invented a language, a programming language called Logo, which was designed to teach computation ideas to kids. And he actually coined the phrase computational thinking some decades ago, and has mentioned it in lots of his works. He was very interested in sort of infusing the general education mechanism with these computational ideas. And there were others that had that same kind of early instinct. But it was in the year 2006 that Jeanette Wing, who many of us at MIT remember fondly from her graduate student days there, Jeanette Wing published a short, couple-of-page piece in the Communications of the ACM, making the argument that these computation ideas, these ideas that are at the fundamental level of computer science, are not just for computer scientists, they're for everybody, and that we should infuse them in everybody's education. Well, this was an interesting piece, and I highly recommend that any of you who aren't familiar with it go back and read it. It immediately resonated with a large number of people, many of them computer scientists, but a number of other people involved in education. And it basically caused an explosion of activity and reaction. So immediately after Jeanette Wing's publication, there were books written about computation thinking. There was lots of papers published. There were centers opened in universities researching the idea of computational thinking, infusing that in various educational projects, and so on. They're just one thing after another, and that explosion is still going on. There are people who are betting their careers on this idea of computational thinking. It made a huge, huge splash in the community. So, we are all familiar with the impact of computational thinking on various other non-computer science topics, okay? Everybody has their own list. Just to mention a couple of them, there's economics, okay? There are companies like Rholesia, I mentioned up there, that are basically impacting the real world of business by mechanisms of macroeconomic simulation. There are, there's simulation technology and game theory. There are things like pricing models. A few of you might recognize the equation for Black-Scholes there that determines the value of an option by a strictly algorithmic approach, by which you can, synthesize an equivalent instrument by means of a carefully constructed algorithm. And there are many other things. The little graph there shows the flash crash, which was an interesting phenomenon that's still being studied from an algorithmic standpoint. We all are aware that biology is basically becoming an information science, and there's a lot more to say about that, but I won't go into that here. There's even a lot of computational thinking that's invading things like the arts. And some of these are really quite interesting. It's often said that abstraction is the science of art, and other people say that computer science is the science of abstraction. So somehow in my mind that makes computer science be the grand science of art, or something like that. But there is a relationship there, and there are many interesting things going on, even in the sort of commercial sector. We see companies like Netflix and Pandora and so on that are building sophisticated models of people's taste to be able to predict what movie you want to see next or what kind of music you want to listen to. And so that is actually affecting the world that we live in. There are companies like Epicogix that actually are building systems that are very sophisticated in modeling various aspects, including taste. And there are companies that are making real go, no-go, green light decisions on whether to produce a film based on some script by, using Epicogix models, or whether to come out with a product, and so on. So that kind of impact is happening everywhere, and in many, many other arenas as well. We can also find some examples, some of them quite strongly motivated, of great thinkers who actually had some element of computer sort of algorithmic thought that we can discover, despite the fact that they predate computers. So this guy you may recognize, maybe you don't recognize. In fact, it's James Clerk Maxwell, okay? One of the greats in physics. The great thing he did was to consolidate a bunch of work of others, of Ampere and Gauss and so on, into what we now call Maxwell's equations. We can kind of view those in retrospect as being sort of the lines of code that run the basic physical universe. So he looked at those lines of code and tried to make them look pretty and symmetrical and everything. And one of the things that ideas he toyed with is changing them just a little bit to have a sort of a symmetry between the handling of electric fields and magnetic fields. And this symmetry led to the idea that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. Okay, so there's sort of a circularity. There's a self-perpetuating phenomenon that he predicted just because of this aesthetic fix he made to Ampere's law. And it turned out that that phenomenon he would propagate at some speed that he could predict because of his model, and that speed exactly matched the then measured speed of light. So there was a eureka moment, a big eureka moment in physics, when Maxwell explained light, the propagation of light, as an electromagnetic wave. Okay, there are others that we can point to. Einstein has a whole host of them. One is this mystery that he was hell-bent to solve about why is the speed of light constant? Why do two people moving at different speeds observe some experiment, and to both of them, it looks like the speed of light is the same, okay? That's basically kind of an algorithmic mystery that he was able to solve by special relativity. And he asked questions like whether God plays dice with the universe, okay? A modern computer scientist would say, does the universe run on a randomized algorithm? Okay, there are some other examples that we can point to of places where there were great thinkers who obviously needed computer thinking, but didn't have it, okay? This goofy-looking guy turns out to be René Descartes, one of a very large number of very smart people who were completely baffled by this thing that they call the mind-body problem, okay? The relation between, the arrangement of atoms in my physical body and kind of the consciousness that kind of uniquely defines me. Okay, this was a great mystery in philosophy. I remember taking philosophy courses and studying it. It turns out that to a modern, educated computer hacker like me, okay, that's not a problem at all. Well, by the way, this is a picture that Descartes drew to make the whole thing clear. It clearly didn't make the whole thing clear to me or to very many other people. But to a modern computer-savvy person, there isn't much of a problem, okay? We have much richer set of models. We know about hardware versus software, okay? We can understand about a process that has information stored as transient state, and so on, okay? And all of this kind of goes away. We kind of can understand the distinction between the physical arrangement of atoms in a body and the sort of consciousness and behavior that they're exhibiting. So, in fact, this has become an uninteresting problem because of the impact of algorithmic thinking. Okay, let's mention a couple of things. The four of us are all university professors, and so how does this impact university education? Well, it is having an impact, and I'm going to just mention a couple of very quick data points. One is a proposal that was made by two of our colleagues, Professors Adler and Sussman, decades ago, that MIT actually teach electrical engineering, okay, not in the traditional way, but by teaching our students to write programs that simulate electrical circuits. And the theory was that if they really understood how to write programs that behave like electrical circuits behave, then they would now demonstrate they understand the electrical circuits. A very interesting and radical approach, educational approach. It never quite got off the ground simply because MIT didn't want to, was conservative enough, maybe with good sense, conservative enough not to risk its #1 rating in electrical engineering on this kind of a very risky experience. I wish that we had found a way of doing that experiment, and things like that may happen in the future. Another thing that those of you who are intrigued by this might look up is there's a course that's gotten a lot of press taught at Princeton. It's called COS 126. And what that does is it's nominally, I guess, a course in programming. But what it does is it has a series of labs that are fascinating, okay? These are the kinds of things that are done traditionally in sort of wet labs, where you take real hardware and you go into the laboratory you make something happen, and you mix things together and measure things and come to various conclusions about various domains in science. But each one of the Princeton labs does precisely the same intellectual exercise, but does it using computers. Okay, it does it using simulation or other sort of programming aspect. And this is really the essence of computer science. And the essence of computer science, in my view, is the idea that you can understand something by some physical structure, by extracting, by encoding that physical structure as a string of bits, as information, and processing the information rather than having to process the structure itself. Okay, very strong algorithmic thinking component to that course. Okay, there are various things happening in earlier levels in education. I'll just mention a couple very quickly. There are things, lots of languages and lots of sort of toy environments that are designed specifically to kind of enrich children's understanding of computer ideas. Many of us are familiar with those. There's a bunch of kind of online models and resources, which one of my favorites is something called Computer Science Unplugged. I don't know whether any of you are familiar with that. But the thing that's interesting about this is a site that is dedicated to computer science ideas for kids. But it doesn't use computers at all. So it has sort of physical analogs that demonstrate these computer science ideas. Okay, and there are many others we could name, but one of my favorites is games. Okay, most parents I know object to their students devoting a lot of time to computer games, but I find that at least many of them are a really rich educational experience. Okay, many of them involve the simulation of some world, like the world of goo is one of these things. There, it's not a real world. It's not an accurate model of the physics of our real universe, but it is a world that has some model and some laws of physics, and the students, the kids who play with this, all of these simulations, spend a lot of time kind of reverse engineering the rules that these universes run by. Okay, they're actually learning lessons in computer thinking, although it's perhaps a little bit subtle and often escapes the attention of their parents. Okay, so for those of you who I haven't yet convinced I'm completely crazy, let's go to sort of the cosmic view of algorithmic thought in education. You're all familiar with these simulation games. Okay, we know about various sims and so on. There's hundreds of simulation games at this point. They have things like simulated people. We call them sims. The people actually have characteristics that are loosely modeled after real people. In many cases, they simulate hunger. They simulate pain. They simulate lust, love, and all kinds of emotions. Okay. Now, it is true that all of these simulation models are very primitive. But we've only been doing this for a decade or two. Okay. These simulation games haven't been around for very long. So they're kind of understandably primitive. But imagine, after another few decades, imagine 100 years of evolution of these games that have simulation models of people. These people would get more and more sophisticated. Maybe they'll get so sophisticated that they'll start wondering about the lines of code in their own implementation. Could that happen? Could they get that sort of reflexive instinct? Well, maybe they will try and understand the lines of code in the game and kind of reverse engineer the environment they're in. Well, one thing that we could kind of muse about is maybe that's the situation that we're in. Okay, maybe our scientific exploration of physics is basically trying to understand the lines of code in the physical universe. Okay? Our study of DNA and its relation to our behavior. Maybe we're sort of reverse engineering the code that implements us. Okay? So there's this sort of strange view that we have a universe that is following some algorithm, and we have gotten sophisticated enough that we actually can have as a goal the understanding of that algorithm and the prediction of its behavior. And there are all kinds of, kind of interesting games we can play with that idea. We can imagine that, for example, the Big Bang, okay, we have a lot of evidence that there was a Big Bang 13.5 billion years ago, okay? Maybe that was just the time of the last reboot of the universe, okay? And maybe whoever it is who hit Control-Alt-Del and caused that reboot, maybe it was a 13-year-old kid. Maybe it was a system operator in some higher level universe. Okay? Maybe that's the person that some people call God. Okay? Lots of kind of interesting issues. Okay? Our prayers to our God, are they in the nature of bug reports or feature requests to whoever's kind of running the universe that implements our behavior? Well, you can listen to this and nod politely and say, this is just crazy. And you're right. It is just crazy. And on the other hand, one of the things I like to do is to defend craziness. So let me defend craziness a little bit. Maybe I'm defending myself in the process. One thing that's kind of fun to do is to take a bunch of ideas and put them on a spectrum that ranges from boring on the left to insane on the right. Okay, now we can all play this game and we'll all put ideas in slightly different places. Okay, but there are a lot of things we probably agree on. Okay, most of us will agree that accounting is pretty boring, right? Have I offended all the accountants in the audience? And we might agree that, invasions by space aliens, well, that's pretty crazy. Okay? Well, suppose we start getting things that are closer to the center of the spectrum. Can we find a line that divides ideas that are profound from ideas that are just crazy? Okay? Where is that line? And my thesis is that there are things that are close to that line on either side of it. And there's kind of a fuzzy region around that line. But the things that are close to that line and on either side of it are kind of the most interesting ideas. So the ones that we argue about, is this a crazy idea or is this a profound idea? Okay? Those questions are the most important questions we ask in some sense. And I actually think that one of the great skills we can give our students is to be able to explore that center area of the spectrum, to occasionally go over the line and explore crazy ideas. Okay? That's the way in which they get to be able to distinguish crazy ideas from profound ideas, which is a terribly important skill. Okay, so creative thinking, I think, involves a lot of exploration on both sides of that boundary, and so I will forever defend the exploration of crazy ideas and the teaching of that exploration to our students. And I will argue that algorithmic thinking is an essential tool for doing that. Okay, so I don't have a lot of time left, and I haven't said anything about what we should do about all this. I've been rambling on. And one answer, I don't have a prescription, by the way, so this is a short one-slide pitch. One thing we can argue is we don't have to do anything. Okay? This is a movement that is more powerful than any of us. Okay? It's going on anyway. It's going to go on. It is a conceptual revolution that is inevitable. Okay? I believe all of that. On the other hand, I also believe that I want my children and my grandchildren to be kind of on the leading edge. Okay? We all want our universities to be producing the leaders of the next generation, not waiting until some other group of people leads them in the direction of computer thinking. So we kind of like to get a jump on that. Okay, so one thing we could do the four of us are college professors. Many of us here are college professors. One thing we can do is teach courses for sort of using computer science ideas at the university level. Well, that's pretty easy for us university professors to do, and a lot of people are doing that. The problem is that the people we get coming into a university like MIT, for the most part, already have gotten this skill. They already understand about computerized thinking and sort of internalized it. And in fact, what we need to do is to influence that pool. That we need to start much, much earlier. We need to get younger kids thinking in computer terms about various things. Okay, so the problem with that is that there's a sort of generational time constant. One of the things we can do is to make that happen is that as university professors, we can be teaching the people who are going to be high school teachers, for the next generation. Okay? But that's a long time to wait. We have to teach these teachers, wait until the old teachers retire and get replaced by the new teachers that we taught, and then wait until the kids that they teach get out into the workforce and start changing the world. Okay? That generational time constant is kind of a killer. So there are various things we can do to try and avoid the generational time constant. One of which is that we can make a movement to try and re-educate the current high school teachers. Take the high school teachers, give them courses, get them to think in computer terms more than they're doing now, and that probably is a help. Okay, there are a number of potential problems, one of which is that once we make our high school teachers computer savvy, they may all get job offers from Google at 3 times their salary and disappear from the teaching pool. So that's something to worry about. But basically, the thing that I think it's important for us to do is, for us as university faculty and people with educational research objectives, is to kind of fuel the fire. We need to develop tools. We need to explore ways of getting computerized computer thinking into our non-computer science curricula. And I think that is an important conceptual revolution. Okay, so just to kind of summarize, we have, from the world of computer science, we have new tools for teaching. We have new tools for learning. And I think that we have, as an equally important part of this triad, new tools for thinking. And that is, in fact, impacting what we should be teaching our next generation of students. Okay? Thank you.
Thank you, Professor Ward. The next talk